So we've been talking about energy and the laws of thermodynamics. And what we want to head towards is understanding how the direction of a reaction is determined. And so to get that full story, we need to look at the total energy of a system rather than just these examples of energy and entropy. So don't get intimidated by this equation. It's just telling us that the total energy of any situation, whether that's me holding up this pencil or whether it's reactants in a reaction, that the total energy in that situation or system is equal to something called the free energy, which is what G stands for. And actually, let me write this over here. I'm not going to fit it there. So the total energy is equal to the free energy plus the temperature, so T you're all comfortable with, I think, times the amount of entropy, which is what S stands for. And remember, that's our measure of disorder. So the total energy includes entropy, which is the disorder, and also this thing called free energy. And these are important because we could also call these more broadly usable energy and unusable energy. So the total energy is broken into usable energy and unusable energy. This is important because, like the name suggests, this is the energy that can be utilized by the cell. And so this becomes the energy that we're going to focus on and that we're going to talk about how it determines the reaction. So we're going to focus then on free energy. So this is just a reorganization of that equation that we were just looking at. And then if you're not familiar with this, the delta symbol means change in. So let me put a chemical reaction here again. So these are my reactants. These are my products. So there is a certain amount of free energy or usable energy associated with A and B. And so we could call that the free energy of the reactants, or R for short. And then there's a certain amount of free energy associated with C and D. And I'm just going to abbreviate that as the free energy of the products with a little p. So the free energy change is equal to the difference between those. So the free energy of the products minus the free energy of the reactants. So if a reaction is a spontaneous reaction, then it will have a negative free energy change. That means that the reactants had more energy than the products. So let me put some numbers in here, and this will hopefully make this a little simpler. So imagine that I had 20 units of energy in my reactants, and I have only 10 units of energy in my products. So I have more energy in my reactants, less energy in my products. If I use this equation, then I have 10 here minus 20. This would give me a free energy change of negative 10. And so this would be exergonic. Remember, energy just can't disappear. It has to go somewhere. So this becomes energy that becomes usable, that's released for work in the cell. So because this energy didn't have to, there was more here than there is after. So you could also, if this is helpful, think of this as a before and after. I had more energy before, I have less after, so that energy must be able to go somewhere and be used in the cell. So these are spontaneous reactions. This is the direction that will occur on its own, kind of like the crystal dissolving, and it is able to release energy to be used by the cell. So that energy is going to be able to go somewhere else. Remember, energy is not created or destroyed. It's just going to be able to go into something else and be used by something else in the cell. If I change my numbers here, so let me make the free energy of my reactants 10 and the free energy of my products 20. Now, I got confused there for a second. So Now if I do the equation, I'm going to take my products and subtract the free energy of my reactants. That gives me a free energy change of positive 10. So that means before I had less energy, after I have more energy. So remember, that means that that energy had to come from somewhere. Energy can't just be created. I can't just have more now. So that's going to require an addition of energy. So if there is a positive free energy change, if that number is positive, that means there had to be an input of energy from somewhere, because energy is never created nor destroyed. It's changing forms. It's going to have to come from somewhere. This kind of reaction will not happen on its own. It's not spontaneous. And so, again, this is going to be because there has to be an input of energy. And so if you want to compare this back to chapter 5, this is a lot like diffusion. Diffusion is a spontaneous process. It happened on its own and doesn't require an input of energy. And in fact, it's a source of energy in the cell. An endergonic reaction is more like active transport. You had to put in energy to make it happen in that direction. So again, a spontaneous reaction has a negative free energy change. So negative delta G. So that means it's able to release energy to be used by the cell without any additional input of energy, and that's the direction that the reaction will occur. It doesn't mean that it's fast. So sometimes in our everyday use of these words, we think of the term spontaneous meaning fast, but it's not. Okay? It could take 1,000 years for it to happen, and it could still be spontaneous because it's a negative free energy change. So this is an example of a exergonic negative free energy change. And I didn't mention this earlier, but as far as remembering these, exergonic, think energy exits. So exergonic exits. Okay. Endergonic is the opposite. Think energy in. Energy has to go into that reaction. This is an example of an exergonic reaction. It's the breakdown of ATP. So it's taking a molecule of ATP. This is the A part of it. So the name is abbreviated, adenine for the A, and then TP is for triphosphate. So there's 3 phosphate groups on there. And when I break it down, I only leave 2 phosphates. So ADP is the adenine, and then di for 2 phosphate, plus a free phosphate, which is abbreviated as PI, so a free floating phosphate. So ATP is my reactant. These are my products. This reaction, I'm just going to rewrite it here for simplicity, has a negative delta G, and to the tune of negative 7.3 kilocalories per mole. So kilocal is like a calorie, so this is actually the measurement that's used on food. So again, this is an exergonic process. It's spontaneous. It releases energy that is going to be used by the cell to carry out a large variety of processes. For example, we talked about muscle movement already this semester. ATP is in your muscles, getting muscles to move by carrying out this reaction. So when you think of your muscles as using energy, this is the energy that they're directly using. You're going to have to create ATP using energy in food. So that's an energy transformation. The energy in your food will be transformed into the energy in ATP, and then your muscles can use the ATP energy. If I want to make this reaction go the other direction, so I'm changing the direction of my arrow. So this now becomes a positive free energy change. And in fact, it would be positive 7.3 kilocalories per mole. So that's because each side of the arrow has the same amounts of energy. It's what is the products and the reactants that changes. So by changing the direction of the arrow, I change this into a positive free energy change. So that means that energy has to go into this reaction. So if breaking down ATP releases energy, then making ATP will have to have an input of energy. So I mentioned a moment ago that ATP hydrolysis, which is exergonic, is going to provide energy for other things in the cell. One of the things that it can do is provide energy for endergonic reactions. So exergonic reactions, again, they release energy. And endergonic reactions have an input of energy. So if this is releasing energy, it can feed in as an input of energy for an endergonic reaction. When that happens, it's called energy coupling. And it has to happen at the same place, at the same time, for the two reactions to be coupled. So we'll look at an example here. This is two different reactions. So over here is our first reaction. It's endergonic, positive 3.3 kilocalories per mole. It's taking a glucose, which I'll just simplify the structure here, and adding a phosphate onto it. And it's making a molecule with a phosphate stuck onto it. So this is, again, a positive free energy change. So this is endergonic. It's going to take an input of energy. ATP hydrolysis, we have ATP getting broken down into ADP. And remember, we said that this is exergonic. It's going to release energy. So the energy released here can provide the energy for this reaction. And notice that if they're coupled, then I can combine the values. So positive 3.3 and negative 7.3 gives me a total free energy change for both reactions of negative 4.0. That's exergonic and spontaneous. So by putting these two reactions together, I can provide the energy for this reaction. How do I put the two reactions together? They have to happen in the same place at the same time. How can that occur? It has to be in the same protein. So the protein, if I imagine this is my protein, it's going to have a place for glucose, a place for ATP, and both reactions will happen in the same protein at the same time. And that will couple the reactions, again allowing for the free energy change to be negative for the coupled reaction and for this whole process to go in this direction. So to summarize, the direction of reactions is determined by the free energy change. If there's a negative free energy change, that means that energy is released from the reaction and that energy can be used by other processes. If there is a positive free energy change, that means an input of energy is required. In order to make the reaction go in that direction, energy will have to be provided by some other reaction in the cell.